In this section, we're going to look at the structure of the atom and how the discoveries were made that led to what we know as the different parts of the atom today. So these are some of the ideas that helped in the development of the current model of the atom. We've talked about Democritus. We'll look at what's called the plum pudding model, all the way up to quantum mechanical model. So first of all, the atom we know is the smallest particle of an element that has those same properties of that element. So if I have carbon and I have one atom of carbon, if I break that atom down, I no longer have carbon and the properties of carbon. So when Democritus coined the term atom, what did we really know about the inside? At that point, they didn't know much at all. They didn't have the technology to know much about the inside of the atom. That came along much later. So there wasn't much known about the insides of an atom until J.J. Thomson started looking at some of the ideas that he thought about what might be inside the atom. So he used what was called a cathode ray tube, which was kind of like a beam of light, but they weren't sure about all the properties that it had. So they shot this beam of cathode rays through this vacuum tube. It's a sealed tube with nothing inside. And then they looked at what would happen. And then what the man in this video is doing is he's got a magnet. And I want you to look at what happens to this beam when he holds the magnet near. Now keep in mind, if it was just a ray of light, it may not behave this way.
Okay, this is a cathode ray tube. What it essentially is, it's a vacuum chamber. There are no gases inside this glass tube. The only thing we have are two electrodes. One's called the cathode, the other's called the anode, and a fluorescent screen in the background. It's coated with some type of fluorescent material. When I turn the power supply on, we'll see a beam that causes that fluorescent screen to glow. Looks like a nice straight line, doesn't it? We call that a cathode ray because it emanates or begins at the cathode and shoots across over to the anode. J.J. Thomson was working with cathode rays. We really didn't understand what they were. I mean, we have electricity going in one side and coming out the other, but there's nothing inside to conduct it. It's a vacuum tube. So he decided to apply a magnetic field to this cathode ray, and he found something interesting. We apply one pole of the magnet to this beam, and we'll see what it does, and then we'll flip it around and see what the other pole does. This is my favorite part. Can you see what's happening to that beam?
So if you notice, as he moves the magnet towards the beam, it tries to repel.
It's being repelled, isn't it, by the magnet? We flip the magnet around, and what do you think is going to happen this time? Well, if it's being attracted on one pole, see how it's being attracted there? Let me rotate it so the kids on this side of the room can see it. See how it's being attracted there? And then the other pole, do you see how it's being pushed down? What does that tell me about that beam? It has a what? It has a charge. Let me tell you about the poles of the magnet. The one that pushes it away is the negative pole. So what does that tell you about the charge of those particles?
So we can see that by using the cathode ray tube and a magnet, we are learning that there is a charge inside of an atom. So when he held the magnet up towards it, the negative end of the magnet, it repelled. So similar sides of a magnet are going to repel each other. So if the negative end of the magnet being held towards the beam caused it to go away and repel, that means that the beam itself must be negative. Another thing that was looked at with this beam was with a paddle wheel in the cathode ray tube. Now again, if we're just shining a beam, it shouldn't be able to do anything to a paddle wheel, like if you think of a paddle boat. But watch. So as the beam is turned on, it's causing that paddle to spin. So that means that the beam must have some type of mass that's causing that wheel to turn. If there was no mass to it, it would just be like shining light on that. And so now we know that atoms have some sort of negative charge and they have some type of mass. So by using that cathode ray tube in the late 1800s, we were able to discover what we now know is the electron. And we learned that it has that negative charge and that has a mass. So using that cathode ray tube, the cathode ray tube is going to pass that ray from one end to the other, and it's going to travel from the negative end to the positive end, just like when magnets, positive and negative attract each other. So, like we said, those experiments show that there's a shadow, which shows some type of substance there. The paddle wheel showed that there was mass, and the cathode ray deflection also showed a charge. And so again, that led to the discovery of the negative charge of the electron. And so this is the man that did that, J.J. Thomson. And so later they were named electrons. So at this point, how would you draw the model of the atom? So all we know is basically that it's, some type of spherical object in theory, and it's got this negative charge somehow throughout. But we also know that overall it's positively charged. So in addition to those negative charges, there must be positive charges as well to keep it overall a neutral type of atom. So Thomson developed what was called the plum pudding model. Now, most people today, I don't really know if they know what plum pudding is, but if you think of a chocolate chip cookie. So the cookie dough part would be the positive part of the atom, and the chocolate chips would be like the negative electrons spaced throughout. Then we have Robert Millikan, who our Millikan University in Northern Illinois is named after. In 1909, he determined the mass of the electron, which was 9.109 times 10 to the negative 31 kilograms. So 0.000309 kilograms. And he also confirmed that negative charge. So because of that, we knew if there's negative, there has to be positive. But we also know that the electrons are very, very small compared to the total mass of the atom. So there has to be some other substance, some other thing to account for that mass in there besides the electrons. So then what was done was called the gold foil experiment. They took a piece of gold foil, which would have atoms lined up next to each other, and they were going to shoot a beam through to see would that beam all be able to pass through, or would something bounce back? So this is the contraption they used. So this would be the gold foil, and then they would shoot the beam through to see if it would go all the way through that gold foil, or if there was some massive substance in the atoms that would cause it to bounce off. And this is what they saw.
In 1910, Rutherford and his co-workers were studying the angles at which alpha particles were scattered as they passed through a thin gold foil. Most of the alpha particles passed through undeflected. However, a few were found to be scattered at large angles, some even back in the direction from which they had come. This meant that they had collided with an object much more massive than the alpha particles themselves, yet so small that only a few alpha particles encountered them. This atomic level view shows what is happening. Most of the atom is occupied by the low mass electrons. The nucleus is small and massive. When an alpha particle encounters a nucleus, it is scattered at a large angle.
So by doing the gold foil experiment, they saw that most of the particles went through, but every once in a while one would bounce back. And so when they saw that just very few bounced back, that meant that those masses that they were hitting were spread out far apart from each other. And so if we look at the contraption, most going through, but a few bouncing back was what they saw. This showed them that there had to be some very densely packed bundles of matter within those areas, and they must have a positive charge to repel the positive particles that they were sending forward. So if we're comparing the Thomson model, the plum pudding chocolate chip cookie dough model, with Rutherford's model, we can see that with Thomson's model, the electrons are spread throughout and the positive charge is also equally distributed throughout. With Rutherford's model, after the gold foil experiment, they determined that the positive particles are centered in the middle, or what they now call the nucleus of the atom, with the electrons spread out around it. So the nucleus is very, very small compared to the total size or volume of the atom, but it's the most massive part of the atom. Size comparison, if you think about a marble placed in the middle of a football field, that would be the equivalent of the nucleus to the whole size of the atom. And Rutherford at that time suggested that the electrons are going to orbit the nucleus like planets around the sun, which often that is a way that is described for a basic model of the atom, but as we go further, we'll learn that it's a little bit more complicated than that. So looking at the proton is a subatomic particle. It's located inside the nucleus, and it has the positive charge. The electrons are located outside of the nucleus with a negative charge. And then the neutron is a neutral particle that is also located in the nucleus. So the nucleus is made up of the protons and the neutrons. The nucleus has an overall positive charge because of the protons. The atoms are going to have an overall neutral charge because the protons and the electrons will cancel each other out. And almost all of the mass from the atom is going to be located in that nucleus because compared to the nucleus and the protons and neutrons, the electrons have almost no significant mass at all. So when we're looking at different types of elements, the number of protons that an element has determines the type of element. So if we're looking at a carbon atom versus a nitrogen atom, what is going to distinguish them will be the number of protons. Then we have what are called nuclear forces, and these nuclear forces are very, very small, short-range forces that actually hold those protons and neutrons together inside the nucleus. And lastly, the size of an atom is based on its radius, so the distance from the center of the nucleus out to the farthest electron. And this is about 40 to 270 picometers.